Start. So, aim of this course is to study some objects active in this, some objects for this class. And we will study what are called concepts and aim is to study the representation of mostly commutative diseases and try to prove what is called spectral theorem for a normal bounded argument. So along the way, we first prove spectral theorem for the self-adjoint. Then by coming into the field of self-adjoint, and using that we prove for normal, and for a coming into the field of. So this will take nearly half of it, strictly more than years. After that, we can do some unbounded operations, and that also involves sister regular. We will involve something sort of command numbers. But I may not specify, it's not really needed. But we can keep this without any. This is actually command number. But then the profile is close to the these are all contained in the they are all so to prove spectral theorem for unknown operations, we use these are also. But we need not do that. If you are interested in something else, you can. Spectral theorem or bounded normal operator is certainly there. After that, if you want to, if you are interested in something else, if you are taking it for credit and then you can do it. So that is the idea. So what is spectral theorem? I'm sure all of you know spectral theorem from the matrix normal. So if we have a C in C, and P is normal. That is, it comes with this. Then it can be diagnosed. Then it can be diagnosed. Meaning, that is the unique operator, unique matrix. Such that I have P is equal to U lambda 1 is lambda n theta. Yeah. The lambda 1 is lambda n. This is spectrum. The spectrum is this lambda 1. And this U can also be explicitly written. This is just these are just eigenvalues of this P. This normal matrix P. It's a complex number. We will mostly consider all our vector spaces, all those things. We will mostly consider one of those complex. If we deal with real number, then specifically, and if they don't say anything, it's not the field is coming. Okay. So this U is nothing but if say if you want to this is for P is a matrix. And this matrix and operator, you want to write it in constant terms, then it's matrix. This matrix is with respect to the usual orthonormal. One, it's the one like this. So it is the usual orthonormal. This just stated the diagonal operator, which is another orthonormal. That's what. Whereas U is the unitary operator is something which is orthonormal. Orthonormal basis or this. We will depend on it. We will depend on this. So, if this is the usual standard, and if you have a problem, an eigenvector, where the n eigenvector, and they will also be orthogonal to each other. This U is just from this is just U of this is, this determines operators. You will depend on the basic that determines operators. So, this is what we use. So, Any normal matrix T is actually a function on this one of the this one. I mean, if you take this set, this omega is going to be one of the a matrix is just a kind of an normal matrix is a function of the one of the once you fix an orthogonal basis. But once you change the orthogonal basis by T, then it's a different orthogonal. So in this sense, this matrix is a generalization of functions. Functionally, you fix this now only number of things. Just have to specify the many numbers, lambda of lambda. This is a question. Right? And then here you have to fix an orthogonal basis. If you change the orthogonal basis, you will be different. So all these orthogonal operators is non-commutative, kind of non-commutative generalization of functions. Okay? And that's why we will see as but it's all generalization of functions. Okay? And they follow this space. So that's what we want to see. So this is about the just a linear matrix. We want to prove an infinite. We want to prove an inverse space. We want to define operators in the inverse space. We want to prove the general operation in the space. We want to prove in the and there we won't have eigenvalues. We will not have spectral in defined, but something is spectral. We are in eigenvalue is something P of x equal to lambda x. We did not correct it. Some non-invertibility is condition with the that's what that's because if you have an operator which is 1 like in space, you see that. If you automatically, I mean, it's 1 it's a decimal. So that condition is so I will recall graduate analysis measure theory is something that is requisite for us. You need to know measure theory. And you need to know some basic concept for the reverse. So I will recall some of them. Some of them I will prove, some of them I will just take it. You will anyway see some of them which I think I'm not sure if it is done in the graduate one or two. So other than that, you will just continue. Even if it is not done now, graduate I encourage you to attend graduate too. So I mean, so that. So, if you recall what a couple of cases, we will always denote H as equal to and V of X is all bounded object. I will define it bounded object on X. Or we define it V of X and K are different here, both then we will not consider non-closed as complete. So when we definitely is all over. So what is it? Let's start with practice this. The reason I am taking this is I want to state an identity for the data. So H is just the linear space and electric space. This is the then a two variable function. One is P. The two variable function. It's said to be, I mean, if it is linear in both, it has two variables. If it is linear in the both variables, it's called bilinear. But we will not assume linear in this variable. And so this is in mathematics, linear products are linear in this first variable, 19 linear in this variable. If you are doing physics, it is the other way. That's the right thing to do. Somehow we are used to it. So we follow this. Okay. Actually, it's better to have this conjugate linear this. So okay, this is the linear space, and this is actually what is called as a linear form. If it is linear, the first variable conjugate this. So I write down what it is. It is linear first variable. Linear. The second one. I hope you know what you mean. So I will have. So then this is the exercise. When you see it. So use this linearity and conjugate linearity to verify the problem. So for all Fy, we get this 4 times Hy equal to relation A equal to 0 to C. I use the comments. Well, not in this. I use it. Yeah, look, I'm got a clue, right? Usually, when you have a real product, it's uniform. We will write this as a norm, right? So this is like same repeating. So this is like a norm. That is a real product. This is something connecting the norm. If you have a real variable.
Is this the first and parallel?
No, this is not. This is called polar. Polar parallel is something. This is not variable.
Yeah.
I will come. This is not parallel. I mean, for real value, you have something like this. 4xy equal to. For real, for vector space of over, real product over here, you have something like this. I think, for square minus just like this. Okay. But that will not be satisfied. You get real path as well. So that will not work. So that is your universe. So this is it. Yeah, you should verify once you verify. So you will not use it. So you can just use the area, I think, take it out and actually do things that. Okay, we'll use it later. And circular form is inner product, semi-inner product. Linear form. It's semi-inner product. We will use this sometime. It may not be inner product, it will be the semi-inner product. Yes. This is for the circle per channel. For the circle per channel, x y equal to x bar. Why is this circle per giant? If you have a matrix, if you have some fixed vector x1 to xn, okay, then if you take this xi, xj, just remember product between them as a matrix. But I get it. That matrix will be a self-adjoint matrix. If that is satisfied. Okay, that's why self-adjoint. 2x equals just here. Then this is called a semi-inner product. And we define then this will be what is called a semi-norm. This norm arising from the semi-inner product is what is called a So finally, a semi-inner product is inner product. If it is strictly positive, inner product. An inner product. If x like this norm equal to 0, this is for only for 0, this is satisfied, otherwise it is strictly positive. This is what is called inner product. So once you have an inner product, if this is an inner product, okay, then you can define norm x. Then this is set. Then inner product x, right? Is less than or equal to norm x. Like norm. No, this is just a semi-inner product. If you have a semi-inner product, then it satisfies this. This is what is called Cauchy-Schwarz interval. Cauchy Schwarz method. Clear, no? I hope you have seen it in graduate transit one, or you look at something. Okay, this is the basic inequality about inner product, and anything we want to prove an inequality, we use this sometime. Okay? So this is if it is a semi-inner product, that's enough. Then this will satisfy this. And using this Cauchy-Schwarz inequality, which I usually that's CS, if Cauchy-Schwarz inequality, we can prove that it is norm X. Where norm X is never different. Norm X is inner product X. Norm X square is inner product X. Okay, norm X is a norm. Semi-norm. I mean, if it is a semi-inner product, it's semi-norm. Semi-inner product is okay. Is a norm. Or semi-norm. If this is the this is the inner product or semi-inner product. Okay. I mean, you can see this is true because of this. Okay? Now, you have no control over norm of X plus Y when you in a general Banach space or non-linear space. But if the square is something like this, X plus Y, X plus Y, which you can expand. Okay? So you can, this is linear, you can take it at sum of this, so this will become norm X square plus norm Y square. And you will have xy plus yx, which will be 2 times real part of xy. Okay. Now 2 times real part of xy will be less than mod of this, which is less than norm x norm y. And from that you will get that x plus y. This square is less than or equal to norm x plus norm y whole square. So you get the property. So this implies norm x plus y. Because of Cauchy-Schwarz, this is true. Okay. Norm x plus norm y. I hope you have seen all this in this record. So this is the, so once you have an inner product, you have a norm. Okay. And if so definition. Inner product. Okay. Then it is a Hilbert space. If it is complete. With respect to the norm. Okay. Then respect to this norm. Norm gives a metric, and if it b of xy is norm x minus y, and if with respect to this metric, if it is complete, then it is called a Hilbert space. So we will deal with Hilbert spaces. We will also deal with general Banach space. Banach space is just you don't have a norm. You don't have an inner product. You may not have an inner product. Okay, you just have a norm. And if it is complete with respect to the norm, gives a metric, and it is complete with respect to the norm, that's called a Banach space. Now we will deal with this Banach space, which is B of H. What is B of H? It is all continuous B of H. All continuous linear operator between H and K. I hope you have seen this proposition. I will not prove it. T is in B of H. I mean, T is from H to K linear. Then one, T is continuous. T is say uniformly continuous. Then the following are equal. This is my notation for the following are equal. All the following conditions are equivalent conditions. One is equal to C is uniformly continuous. This is equivalent to T is continuous. This is equivalent to T is continuous at any point, or T is continuous at 0. So this is equivalent to direction K such that norm Tx is less than or equal to K times norm X for all X. H. Okay. This is for any Banach space, any non-linear space. It is continuous if and only if it's if it is continuous. I mean, if it satisfies this condition. Okay. This is what is called a bounded linear map. The boundedness comes from this. This is not bounded. Linear maps cannot be bounded as a function. This is what is called a boundedness. Okay, here for a linear map. So this is what is called a bounded linear. If something satisfies this condition is called bounded linear. So I hope you have seen this, seen the proof of this. And we define the noun for an operator. We need an external product. Then we bound it. Then we define non-E. Supreme of that thing. It is not this. Supreme of this is where we define a norm for a linear operator. And provided it's bounded. And this is, then you can see that this norm T will satisfy one of those case. Okay. And this is actually equal to minimum of all K greater than 0, such that it satisfies this condition. That's the right to take any. Okay. So we will use either this condition or this condition, depending upon whichever is used. This is equal to this. So if you are in serious number, I suggest you to go on bring it. It's better not passing this thing. If you are better go through it. Okay. So then this is the total question. With respect to this now, V of X is common. The quotient sequence in V of X. If it is quotient in this now, okay, then it can convert pointways. You can define the mean as now. That operator will be bounded, and that of PL will converge to that operator in this now. That's what this means. That is what we have from this book of this. Huh? So otherwise you can go and see this. So this is a complete. This is a complete. This is also connected. Connect space is a non-linear space. It's a complete. Yeah, that's one. So then I want to recall another thing, which is supposed to be done in we denote this X star, or we have any banana space X star. X star is all bounded linear. It is B of X. All bounded linear. So if we have a extent H, we can define a PX from H to P, right? PVX actually not whatever. We can do by the properties. This is linear. This is a linear. Okay. Then Px using X star. Okay. And the norm of Px, the operator, is equal to norm. So this Hilbert, this H star is actually, so this is the reason as well. It's called lemma, but it's not lemma. What's the if P is in theta, then there exists X in X. That's it. P is equal to P. You can declare another, but this map X going to Px is not linear, it's conjugated. That's what we do. So we can define an inner product on X star. You can define Px. I'm not perfectly because you know it's what just stating just and Y in X. Then this will be a inverted. That is there will be a X going to Px is a bijection which satisfies Px Py equal to X. This which will preserve the inner product. So the bounded linear functions on X can be identified with respect to as with X up to a conjugate linear exponent. It's not a linear. It's not linear. So next we want to define what is called an adjoint. An adjoint is more or less defined as we define it for matrix. Matrices, this is just you take the matrix in B, you just take the ideal element to be the real element, and then take the bar, take the conjugate. So adjoint is defined. They are more or less going to define the same thing. So there exists, if P is a round from zero to A, then there exists a unique we start from B of K second Px one. Px will X is X and Y is K. Pxy is equal to X P star one. You can use the mark to do this. How do we do this? And with just a sketch of this sketch. You consider this fixed y. Then consider this X going to here. So T is linear, the product is linear, this is linear. This is a linear. This is a this map is in this map is in this map is in so because of this, there will exist y, yeah. So this is you call this a linear function. So this will be equal to something, right? And it is z such that it is equal. Okay, and you define is the y equal to and you can see because of this unique law that and if you have it, if you insert a lambda here, if you insert if you insert a lambda here, it becomes lambda. Then go inside again is lambda. Because of this, these are the second verification, these are the but lambda, but P going to P star is conjugate. That is nothing. Okay. So I will list down the property of the adjoints. I don't know whether you have seen this thing in the one, but certainly the school is there accuracy. Proposition. These are the order of that I have written. We will have a look. See, this is the so if you have any of like you have some yes, that is very good. If you have Px y equal to x, y. Then because of the uniqueness, that has to be equal to this. So if you want to verify something for an adjoint, you just have to verify whether this satisfies this. Okay. So because of that, you can identify, you can verify that L is equal to S star. Because if you put S plus P here, and then you will get, I mean, because of the linearity of the inner product, you will get this. Similarly, lambda times P star is lambda bar. Because this is defined in the second variable, you will get a lambda bar. Okay.
And third one is T star star, T double star is because T star star, if you, I mean, T satisfies when you take the bar, if T satisfies this equation, if you put T star here, you get T because of that. Because this condition uniquely determines that. And the fourth one, just T star, you apply one by one. If you have an ST star here, then I mean, you apply one by one, you get T star as that. It's also true that norm of the same as norm of T star. This is because norm of T, how we expect, which is equal to supremum of norm x. This is not one. Actually, you cannot take norm of T to one of this norm here. Right? But norm of any element is norm as a linear function, right? We have this that this function norm of T is equal to norm x. So this is equal to, if you use that supremum of norm x less than or equal to 1, norm y less than or equal to 1, okay, mod of T x y. Norm T is equal to, by definition, because of this lemma, which is equal to this. Okay. Am I going fast? Like this, you will see, I mean, I don't know, you have seen this. Now T is the same like this. Okay. From this, you can have this is equal to x T star, but there is just the bar, you are taking bar. Okay, so because of this, this is equal to 1. Okay. So norm T is same as something. Finally, we have something called C star identity for operators. And if you have any doubt or any problem, or if you find a mistake, you stop me. Norm of T star T equal to norm of T star. This is what is called, when the definition of T star algebra, you will see this. This is what is called T star identity. So we'll do this. And generally, for any operator, ST is less than or equal to norm of square. Follows from that. That's because this norm T is the infimum of all those cases. Okay. The norm S times norm T will satisfy one of those things, right? So because of that norm ST is the infimum of all those things. Okay. For ST, this will satisfy. This will be one of those cases, so this should be like that. Okay. So this is true. So this implies norm T star T is less than or equal to norm T times norm T star. And norm T is same as norm T star. You are very right. So this is equal to 1. You have to prove the other way. So to prove the other way, norm T square equal to supremum of sorry, we want to do the other way. T star T equal to supremum of so we have proved that T star T is less than this. We want to T square is the
Given x.
huh?
Given x square. No, T star T x. Inner product of T star T is x.
Yeah, that's what it will do. I'm just wondering whether it's actually working in the right direction. Hopefully it will work. You are just saying, no, X, Y, right? This is what you are saying. That's what it will do. So norm X. less than or equal to 1, norm y less than 1. And this is equal to, this is equal to, yeah, this is less than that's right. So this is same, this is equal to supremum, you can take the t star out. So this will be txy, tx ty, the mod of this, the same supremum. And so that is less than or equal to. Now we get we get the same way, no? That's what I want to do. I want it the other way. Norm t square is no, I want the other way. This says it gives the same way. That's what I was saying. We have already proved it. So let's compute norm t square. Norm t square is equal to supremum of norm tx, right? Square. That norm x is less than or equal to 1.
Inner product T star T X comma X.
T star t s comma x, and that is less than or equal to norm t star t, right? That's all. So this is equal to that's all. So inner product t star t x x. Supremum. And this is, I mean, norm x less than or equal to 1. And that is less than or equal to norm t. That's all. Okay. So one more thing over there. Kernel of T star, this is linear algebra. You must have seen it in linear algebra. The same proof works here. Kernel of T star is same as radio. I have to say what is better. Okay, I'll come back to this. After defining it, orthogonal. So that's all about adjoint. So now we want to talk about orthogonality. And I hope you have seen the proof of orthonormal basis, existence of orthonormal basis. So we have, so X is Hilbert space. Hilbert space. And if we have two vectors, X, Y, and H, then X is, we say, I mean, then X is orthogonal to Y. We write it like this, is the orthogonal. If inner product of X, Y is 0. S contained in H is said to be orthogonal set. A set contained in H is orthogonal. If for all X, Y, yes, S not orthonormal, let's say orthonormal. So for all X and Y, XY equals 0 if X is not equal to 0. And all those norm X equal to 1 for all X. Okay. This is the normal condition. Orthogonal means they are all orthogonal to each other. And we can easily see that if it is an orthogonal set, then it is linearly independent. And we say something is an orthonormal basis if it is a maximum. So I will just take this. If you want, you can request me. I just prove this in the BSc analysis tool. The video is there. Okay. So I will not do this here. This is supposed to have been done in okay. So take this but no, I want to say this before that. We will be separate industries. If you have a countable, then separate. Okay. So X is separate. Then X is counted. This is also going to divide and norm x square, norm square. And if it is orthonormal, let's say ortho, and ortho, let's say orthonormal, okay, we can divide it into the norm and orthonormal. Then you can see that the distance between x and y is, I mean, if this is the parallel, norm square is norm square is norm square, which is equal to 2, right? Equal to 2. So the distance between any x and y is square root of 2. Okay, and it cannot be uncountable. If it is uncountable, then around a ball around something less than square root of 2, you will find something. And there will be a you cannot have how to fit this something. Right? So because if it is an orthonormal set, then it is over. Okay. Okay. I mean, if it is if it is uncountable, then you will have something uncountably many elements around the ball. You will not do, I mean, uncountably many balls. Okay? So you can choose one element in there and you cannot get the countability is there. The cannot be countable. Okay. So now this is the this is the then so the following one, if contained is maximum, let's say right, that is equal to yeah, yeah, countable. So one, yes, is maximal orthonormal. Is the following two for all x in x is equal to summation n is equal to. We have a countable set. This is equal to E1 of P and E1 here to index right has the workers. Okay. Then it's a maximal orthonormal set. Then any x can be determined. You take x, you take the inner product with En. This is a scalar. You multiply with the vector here, and you get this. Right? So you can write it like this. And this sum is an infinite sum. This sum converts to this, and you take x sum, the series converts to x in the norm. Now what is this? That is the way. So this is equal to saying that x y equal to summation equal to these are equal. Now x is all now x square equal to summation x n or so any maximal, so I'm not doing this. Okay. Any maximal orthonormal set will satisfy this condition, equal condition. Okay. And that is what is called orthonormal. Anything satisfied this is orthonormal. Yes. We usually say and it will always exist. You have to use one of them. Maximum. It will always exist. Or even if you have an orthonormal set, that can be extended to an orthonormal. Also, okay. So this I will prove. I want to say, I want to prove the following. If x is equal to space and x naught contained in H is closed. Then you define. And then it's not, but equal to all of exchanges. Calculate. Y equal to 0 or all of them. This is the orthogonal complement. That is called an orthogonal complement. This is called orthogonal complement. So if you have a closed subspace, H is always closed to subspace. We take to those two. It's not in the subspace of the university. Then you take all X which are orthogonal to this, all of this X in the X segment. So all we need is orthogonal to this. So because the product is continuous, this is closed. Right? If X and another is to some X, X are here, and X will also be orthogonal to this because we are not this. So because of that, this is closed. We will close and then then like defined this before. It is also after the nothing is there, like the if you have two Hilbert space, H1 and H2, then you can write this H1 direction H2. You take this, let's say, this all the way. One, y over two. And you can define xy, x1 by 1, x2 by 2, just the sum of this. X2 plus y1 by 2. Or if you take the norm of this, norm will be some square. So this is the orthogonal direction. This is an orthogonal direction. This is the external direction. So this is this will be up to isomorphism. These two things are same. So if you have H, H1, H2 contained in H, then H is equal to H1 direction H2. If H1 and H2 are orthogonal, anything is H1 is orthogonal to H2. And anything in H can be written as sum of something from and for any Z in H, there exists having the X in H, there exists X1, H1, X2, X2, then X is going to X1. This decomposition will be made around. So this is what I call it that the proposition is. I don't know the time to do this. The proposition, have you seen this? You've seen this as well. I'm not sure now how I will say. H not is contained in it, closed. Okay. Then H looks like that, H not that come H not. Of course, H2 are afterward. And everything here can be written immediately as something from you. You've seen this? General inversion is not for time dimension. You've seen this? Huh? I don't think that. No, in general, I mean, in gadget, there is one hundred. That is my question. You have seen it. You know this? You don't know this. Maybe I know this. When did you do this? Last month. My 21. Okay, I will give you one of the scale. So since you haven't seen, no? So I will prove this. Okay. So to prove this, I will use the following. Again, I put 20 minutes. So if we have a K contained in H, a convex set, closed convex set. And suppose Y is in H, then there exists a x naught in K, such that distance between y and K is defined by, for any point, is defined by infimum of x in K d of x. The distance between you have a convex closed convex set. Okay. Then you take the y in x. H. Okay. Then the distance between the element y and the set K is defined with the infimum of x. Okay. And that infimum is attained at some point. Is equal to d of y naught, y naught. What come? I mean, this is a statement. What come? Y naught. Right, this is definition. You have a closed convex subset, and you have a y. Then the distance between y and the closed convex subset is defined by this. Okay. Then that distance is attained at some point. Then that is the proposition. Okay. Proposition is this. See, if K is a compact set, this is clear, right? So, let B equal to that number D is equal to D of K. Okay. Then by definition, this is the infimum of this thing. Then there exists y and x. Huh? There for some there exists. Maybe let's keep y is outside. Okay, like D equal to this, then there exists xn contained in K is equal such that D y xn converges to D. Right? I mean decreases to D. That is that because it's an infimum. So if it is compact set, I mean, then there is no need that this D has to be some I mean, this xn need not converge. This converges to D does not mean xn is converging. But if it is compact set, this xn will have a convergence subsequence, and that will converge to something, and that will give that y naught. But if it is not compact, you cannot do it. If it is finite dimensional, for example, if the K is finite dimensional vector space, okay, then you can take, so if D is this, then you can take a number slightly bigger than D, and you can consider this, say R is bigger than D. Then you can consider this B, Y, R close to 1. You can take it close to 1, and you take the intersection with this. Where that so this will be compact. And so you will have something, I mean, you get using this, you can go. But infinite dimension, you cannot use it. Okay? So for that, we need the following idea. So we have this norm of, so in general, we have for all xy, for all y z, y is for all x1, x2. We have the following. We have this parallel, right? 2 times normal 1 square, normal 2 square. Okay. Here, direct multiplication. Okay. So now I take x1 equal to, okay, let me take x1 next. I want to show that this is the push. Then H is a reverse space. X1 minus x square. That's it. I want to show that this is the push sequence. So this is equal to 2 times norm x1 square, but now x1 square. Now this is a convex set, so xn plus xm by 2 divided by 2 is there. Okay. So that implies norm of xn plus xm square by 4 is greater than 2. Because that is in the convex set. I forgot to say something. Now, see, so you have a y there without loss of generality, I assume y is 0. If you prove it for y equal to 0, then you can shift the set by, okay, without loss of generality. Otherwise, you have to use this y, you have to, minus y without loss of generality, assume y equal to 0. Okay. You consider instead of k, you consider k minus y. Okay. And that will be a convex set again, and that will be closed, and you can prove it, and then you can shift it. Okay. Okay, so now I'm assuming y is 0. Okay, so this is just norm xn conversion. This is g of y xn is just norm. Y is 0, so this is just norm xn conversion. Okay. So I have to prove that xn is actually convergent. To prove that, it's enough to prove that xn is actually quotient. Okay, now xn, so I have this inequality. In this norm, xn plus xm square is greater than or equal to t, because xn plus xm by 4 is in the convex set. Because of that, this is greater than or equal to t. So this will be 4d square. This is greater than or equal to d square. This is greater than or equal to d square, right? So this implies norm. So this term, whatever we have here, this left hand side is greater than or equal to norm xn. Left hand side is greater than or equal to norm xn minus xm square. So I mean, which way I should argue? This is no. This goes to 0, this goes to 0. Okay, and this doesn't go to 0. Now this goes to d square, this goes to d square. Okay, and this is greater than d square. Okay, and this has to go to 0. Clear, no? So this convenes yourself. Okay, convenes xn is quotient. Okay, that's all. So from that it follows that xn is quotient, so xn converges to something. So xn converges to x naught. Sorry, x naught. And that x naught is the requirement. Okay. So now let me do that proposition. H naught is contained in H. Then H is equal to H naught plus H naught. Okay. This is clear? So if you choose a y, you choose a z in H. I have to produce a x from H naught and something orthogonal to this, some H naught per, so that z is equal to x plus x per. Okay. So this is what is called the nearest element in the subspace. If this x naught is the nearest element for this one. That is how you will do this now. If you have something, some element here, how do you orthogonal decompose? You take the nearest element here, you take the nearest element here. Or in fact, if you want to do it decompose with respect to two orthogonal subspaces, if you have something, you will take the element, nearest element here, and you take the nearest element. If you take the sum of those two, you will get this, right? So that's what we are doing. So if you have a z in H, then choose x naught in H naught, and maybe x in H naught, such that d of x naught is equal to d of z H naught. And let x naught, I'm just denoting it as x per. I have to prove that this is actually orthogonal to this. X per equal to z minus x. Okay. Now all I have to prove this x naught is orthogonal to this x. Then z is equal to x plus x prime. Right? I'm just denoting it like this. Okay. Once I prove this, the x perp is actually orthogonal to x, then z is equal to x plus x perp, and it is unique will be clear. I mean, will come to that. The uniqueness all these things will be clear. So, why is that orthogonal to that? So we have to use the property that x is the nearest element to that z. You have to use that property. So we want to consider z minus x. This is the distance between z and x. Okay. This is less than or equal to z. I take the square. Z minus x. Okay. And I can put a minus, plus doesn't matter. Minus epsilon times y. Okay. Y is epsilon. I can put a epsilon times y, right? Square. Now this is equal to, I mean, this is an x square, okay? Z minus x square plus epsilon square mod square minus 2 real part of epsilon y. I mean, this is the x square, right? X square. I have just expanded it. So you have z minus x square, you can cancel these two things and you have only this. So this is greater than this. Okay. So I will so those two equations we get inner product. Let's put it in. No, I have I have the y. Epsilon y yes. Real product. Is less than or equal to epsilon square. That's right. Or what? Yes. Very well. Okay. Two columns. So x is on, so for this orthogonality. So shall I give it as an exercise, the uniqueness and the tail of if you can write it as two different things, you subtract those two things, and the norm will be 0, and they are orthogonal spaces. The norm of that will be sum of this square plus this square, and that will be equal to 0. So each of them has to be 0. Okay. The uniqueness is okay. Then the column will be maybe it's not okay. If it's not, so it's not contained in it. Then it's not double color. It's not first color. Okay. Clearly, it's not contained in it. It's not. I mean, it's not first is orthogonal. It's not. But it's not is orthogonal. It's not first. So this is contained. It's not first. This is orthogonal. So all we have to prove that if you have any element in this double curve, then that is equal to. Okay. So suppose it's not double curve. Then you can decompose this with respect to it's not perfect, it's not double. Right? And what is I have to prove that this is linked, it's not.
How do you decompose H1, H1?
H naught and H naught, right? So something in H naught will be there, something in H naught will be there. And that whatever in the H naught that should be zero. Now Z is the H naught, so Z is equal to X naught X plus X in H naught and X in H naught. That's X plus H naught. Okay. And Z minus, yeah, Z minus X. This is in H naught, so it is in H naught double purpose. So Z minus X. Z minus X in H naught double purpose. Okay. And that has to be zero. Right? Because this is unique or something that is. So from this corollary, we get to the and let's see. If you have any K or any S, and then it is okay. Then, I mean, this per can be defined for any string. It need not be subspace. Then, yes, the S per is a vector space. Yes, it comes that S per is a vector space. It is in fact a closed subspace. Okay. Then, yes, double per. The S per is equal to you take the span of all the elements in S. All the elements in S. Yeah, I take it. You got I think it's